So, main topic here is there's going to be a lot to unpack, but we'll sort of take our time and work our way through it. So, we're going to cover Linux socket hardware, transaction, and receive timestamping in Go. And sort of what that means is how can we get the timestamp at which a packet going across the network is accepted or sent out an actual network card, and when it actually hits the kernel and when it actually hits user space or your Go process. So we'll sort of work our way from like a high level in Go, and then sort of work our way down to the kernel and then the hardware itself. And next slide. So we go like, what is a socket? So like high level pseudo file that basically represents a network connection, right? Like you open up a TCP or a UDP socket. You can treat it like a file, you can send on it, you can receive on it, sort of like you do with a regular file too. But instead of it being a file, it's connected to a port number or an interface card or something of that nature where you can connect to endpoints to send data across. Uh, so what is it like? Let's cover what a network packet is. So like that's just a slice of bytes. Like you follow the rabbit hole low enough, that's all it actually is. And it's all the encapsulated user data wrapped in a protocol header, whether it's TCP, UDP, and then you wrap that again in an address family header that could be IPv4, IPv6, and then you wrap it another last time in the physical layer to specify the hardware address of the actual network cards. And those sort of represent the layers of the TCP IP model. So if you were to Google that model, you'll see these layers represented in the actual stack. And so those are the examples of sort of what you're using at each layer. So if we unpack that a little bit more, you can see at the very top, we have our application layer, which is our Go process. And we say, like I want this web page from this address. So that message gets stuffed into the transport layer, either TCP or UDP, and then it has source port and destination ports stuck onto it. And then we take that entire thing and shove that into an IP layer. And then we specify the actual IP addresses, the source and destination. And then we take that whole piece and shove it down even further into the hardware or the data link layer. And we specify the source and the destination actual MAC address of the network card. And then so that's sort of encoding a packet. You send it out on the wire, and on the other side, the network card will get this whole packet that looks like the one at the bottom and then just sort of reverse unpack it all the way up to the top. So when you do, a con.read or reading anything off of that, you end up with just number 5 at the top. You just get the message itself. You don't have to worry about sort of the layering in the sense, because Go is doing that all for you. So if we look at like a simple like HTTP, which is at at the very top layer, you have a basic handler with a reader and writer, and this just sort of echoes the data that comes in back to the server. So if I curl this endpoint with testing data, I get it back to me. And that's the top layer data that we're sending. Is testing is the data that we're sending across, but we don't have to worry about source destination, wrapping all that stuff down the wire. Go and the HTTP package like sort of does that for you. But theoretically, like HTTP is just sitting on top of TCP. So if we follow the rabbit hole a little bit lower, if we just do like a net.listen on a TCP port, it is a basic echo TCP server. So if we stand this up, we can do netcat to interact with it, and we can send hi on the first line, and it's going to echo it back to us. Sort of what I'm illustrating here is this log print line, as I can capture the time at which I get this data with time.now, and I can convert it to nanoseconds, and I can get the remote address where I got it from. And you'll see the log line down the bottom. Like we get the timestamp, we get the nanosecond representation, and the source where it came from. Since I'm doing this locally, it's going to be my local address, and that's in IPv6 format instead of the standard like 127.0.0.1 address. And you'll notice that the port is just a random port that gets assigned when a client makes a connection. And just for like completeness, we can do the same thing. Instead of TCP, we can do it in UDP, specify that. And we can read from the connection and stuff the data into a packet, into a byte slice, do the same thing, print the time and the source it came from, and we get sort of like the similar output by interacting with it through netcat. And with netcat, you can just like specify -u to do UDP packets. So I will stop right. Is this all familiar? Make sense? I just wanted to like lay some groundwork of like what we're trying to like working our way down to. Does anybody have any questions so far? I don't think you can raise your hand, so you might have to just like start yelling.
So in each of these cases that you've demonstrated here, we're talking about timestamps. Those timestamps are when the next layer of the stack accepted it, right?
These timestamps that you're seeing now are only in user space. So at the very top. So if we look back at the previous slide, we're getting the timestamp at the application layer 5. We don't know what the timestamps are traversing down the layers, but that's what we want.
If we're doing transport layer like you just did, right? Obviously, then it's when we go to IP, right?
Yeah. Well, it's when it's received up. Yep, exactly. Yep. So we know that timestamp basically at the end. So we don't know the timestamp when the packet was hit at the network interface card or when the packet actually goes through the kernel. And that's what we're going to get to next. So jumping ahead. So when we're doing these sort of reading and writings, the TCP connection or the UDP connection, the Go process in user space is making a system call, send or receive, to pass the data from that Go process down to the kernel so that the kernel can use its drivers because it knows how to read it. It knows how to interact with the actual hardware. The Go process doesn't. So you need that layer of abstraction to pass that data back and forth. So like in the diagram here, your app is your Go process. It does reads and writes on the TCP con of the examples I showed you, passes it to kernel space. So that's time that's occurring, going through the socket, the driver, the ring buffers, and then eventually it gets put on the actual hardware on the NIC in the receive and the send queues. And so you could see like those layers as the packet sort of moves further down towards the actual hardware, like that's additional time rather than calling time.now in user space when you call TCP con send. Sometime in the future, it will end up on the actual NIC. Like you don't know when that occurs because it still needs to deal with context switching and kernel passing and those syscalls and all of that additional time for that to actually occur. Yeah, this sort of like covers that. So like, so using time.now includes OS context switching, the runtime, decoding and encoding all those layers as well, sort of wrapping the data in each one of those packet layers. So how do we actually subtract the time that data is in the kernel? How do we subtract the time that the data is spent sitting in those queues? We can use, it's called AF packet. AF packet stands for address family. You can define an actual socket type to create. The problem with that is you then, because you're dealing with such a raw packet, you're then required, so instead of sending data like we did up here with just saying hi, or even up in our HTTP version where we're just passing testing as the data. In this case, we actually need to construct every single layer of the packet. We need to create the IP layer. Is it 4 or 6? Then the transport, we need to, so, okay, is it TCP? Is it UDP? So on and so forth. And we manually have to do that. So luckily, I don't know if you're familiar with Matt Layer. He does a lot of Go socket libraries, one of which is this socket one, which is a pretty broad socket library, so you can specify specific types of sockets we want to create. So in our case, we want to create an AF packet. And the second parameter you see in this code snippet is a raw socket itself. So that we're telling the kernel that we want a raw socket. We're going to construct the packets manually. So just basically give us a file descriptor um, directly to the interface, and then we'll do the layering ourselves. And this socket has the common read from and write to, and so additional methods like you would see on the net packetcon interface in the standard library. So it should feel pretty idiomatic and pretty familiar if you've used that before. So now that we have to actually create these manual byte slices, luckily there's another nice package out there, Google Go Packet, which you can actually just start to layer these things together. So L1 at the top, like we specify the actual Ethernet. So that's what's the source and the destination MAC address that we want to send to. We specify that it's IPv4, and then the next layer, okay, we got IPv4, here's the TTL, we're going to do layer UDP, and here's the source and destination IP addresses. Layer 3 is all the UDP information that we want to do for the ports. And then finally, what we're used to is layer 4, like this is my application data. And then you create this packet, and then you serialize all the packets together, and then you can finally write it to the socket. Whereas before, a standard TCP connection, you could write the slice that's in layer 4, and then everything else magically happens for you. Yeah, so this particular package lets us to easily sort of make those entire layers and construct an entire packet end to end to send to a raw socket. So now that we're using the raw socket itself, now we actually can create raw packets to send back and forth. We could sort of keep going down the rabbit hole here. So how do we actually get those initial timestamps from the kernel? Well, Linux actually leverages control messages that you can listen for to get ancillary information about packets that are going in and out of a particular socket. And you leverage this with the receive message on a socket from the kernel. So that Matt Layer's library socket actually has those methods for you. So in the first case, if I wanted to read incoming data from the receive queue, so I'm doing a TCP con.read. This is the similar read call for the actual socket. I want to read the data, but I also want to read the incoming control message too. So I would get the actual payload of the packet in data, but I would additionally get the packet of the control message that Linux is going to give me along with the packet. So that is where the timestamping information will be. So we'll know that when we got the data, we can unpack the timestamp information to get when it hit the network card, and then when it hit the kernel. And then here we could do a time not now to indicate, well, this is where we got it in user space. And then the other side, it's a little wonky, because if you think about sending data, sending a packet out a connection, the packet will not go actually out on the wire until sometime in the future from when you call this like socket.send or socket.write. So the way that Linux actually handles this for you is once you call a socket.send or socket.write, you have to have another asynchronous sort of listener that say, okay, I'm going to listen for the control messages, but you see where I'm specifying this error message queue? It will sort of loop back that data that you sent out initially. It will come back to you on a different queue sort of internally on the kernel. You could say, okay, so I sent this data out. This is the control message with the timestamp information that occurred for that data that was outgoing. Because if we called time.now and then said connect socket.write, that time.now represents when we actually invoke the method. But sometime in the future, that actual data hasn't actually been sent on the wire yet. Like there might be other packets that were queued up first, but we want to get when that actual packet was sent. So that's how we sort of listen for future information from a packet that we would already have sent out. And so now that we have this sort of control message byte slice from the two queues on the NIC card, we can then parse them. And fortunately, the Unix module has a parse socket control message. And then we can check the headers of that message to see if it matches actual timestamping information. Because there is other message types and levels that represent just different information about packets, but we only care about timestamping information. So convenience, there I sort of made this struct as socket timestamps, and I set the software, which represents the time at which the packet hit the kernel, and then hardware represents the time at which the packet actually hit the network interface card. And you can see like the long little endian decoding is just slicing through the message data at certain boundaries to get the actual in64, and then converting all of that to a Unix timestamp. So while that's all good, as lots of parsing and listening and stuff like that, it was tedious and annoying to do it all at once. So this is the package that we open sourced, this fastAF packet. And it sort of lets you do something like this. So you can query the machine for an interface by name. So ETH0, ETH1, 2, or 3, whatever, whatever's on the box. And then you can say fastAF packet.listen to that interface. You could specify that I want to do raw sockets, and this Unix ETH-P-all that says any packet, whether it's IPv4, IPv6, TCP, or UDP, any kind of data packet, I want to know about it. So you don't have to specify that sort of separately. This package implements the net packet con, so you can sort of use it interchangeably there. But then it does give you convenience methods to receive the TX and the RX timestamps accordingly. Is that a question?
Yeah, I don't know if you're going to mention it later, but should we expect this to work seamlessly if we're running inside Docker as if we're running on bare metal?
It will not work in Docker because Docker leverages the host network stack and network cards. So that's sort of like a bridge. So I do have a demo later on where it's going to utilize Vagrant virtual machines to actually do that. So there is some sort of caveats. So like it's going to be a little bit difficult to use in Docker because of the way Docker does its networking.
It's amazing what you have shown so far. Thank you. Please go ahead.
Oh, thanks. No problem. So once we have this kind of socket, we can have these two convenience methods on top of that. All right, now here's the demo. So what we're going to do is we're going to stand up 2 virtual machines with Vagrant. Each of those virtual machines are going to be pre-configured with a specified virtual NIC. We're going to send packets out a specific NIC to the other virtual machine, and that other virtual machine is going to be doing the same thing. So they're basically ping-ponging each other. And what we're going to see is we're going to just read these control messages from the kernel for these transaction and receive timestamps. The one thing that we're not going to see on here is we're not going to see hardware timestamps because they're virtual machines. They don't actually have real physical network cards. They have virtual ones. So we're not going to get that timestamp information, but we will get software because they technically do have a kernel. They're a full virtual machine. So we flip over to here. Here's my Vagrant. Can everybody see that? I know there's like a show of hands. If a few people want to just say yes, that's stupid small. Okay.
Yes. Yeah.
How about that? Is that better?
Better.
Okay. Cool. So let me get into Vagrant SSH test. AF packet 1. Packet 2. Figure that. Right. So if I gotta go to the share, and now Vagrant. And so I have this example that we can run. Look at the server 1 script. All this is going to do is we're going to build it, and then we're going to run it immediately. We're going to specify that that this ping pong example should listen and bind to the interface name ENPOS8 because that's what the virtual machine assigned to it. Here's the source MAC address and the source IP address, and then the destination is the other virtual machine on the other side. So let's clear that, and then we'll just do sudo server 1. While that goes for a little bit, I'm gonna go into Vagrant example and sudo server 2. So I'm just gonna let this run sort of a little bit and collect up some stats here, and then I'll pause it. I'm gonna go inspect. So cancel that, and then we'll cancel that. Okay. So I am logging out. Each one of these virtual machines is just sending a packet every second to the other one, and vice versa. So they're not echoing each other. They're just constantly probing one of them. So you can see, like on this line, this TX receive message, we're not getting any hardware information because there's no actual network card. So this hardware nanoseconds doesn't make sense. But we are getting software. So we have 2002, 2022 over here. So this is the Unix timestamp at which when this actually sent the packet out from the Go binary, the kernel got it in the future at this time. And then subsequently, we would get the same thing for hardware if it actually had a physical network card. And then on the other side, when it's receiving a message, we are actually getting the software nanosecond right here. And what I'm doing here also is I'm sort of logging out what the user space time that I actually got it in my Go program. And then I just did a diff, and we see a delay. So the delay between the software time and the user space time is approximately 300 microseconds. So what that's telling us is that the packet was in the kernel 300 milliseconds ago until I actually saw it in my Go program. And if we actually had a hardware one, we would see an even larger delay from the hardware side. And so even though we're taking, time.now got a packet and time.now we got a packet, we can still inspect and say, oh, actually, we actually got the packet sooner than that because it hit the network card at one time, and then it hit the kernel, and then it hit user space. So we're actually seeing through the layers when the packet is working its way from the hardware through the kernel up to our Go program. And so we can sort of unpack how that actually works in the example now. And we'll walk through this kind of slow. So that that shell script that I showed you earlier is sort of like just setting these parameters and keeping them in flags. So we find the interface by the name that we pass in. We parse a bunch of information for the addressing. And then eventually we're just going to like skip over the filtering for now. And then we sort of make our way down to let me make this bigger and close that. Make our way down to the listen, where I specify I want to listen on this interface. It's a raw socket for all packets. Now I actually have a connection. And the first thing I do is I spin up a Go routine with a ticker. And every second, we're going to encode a packet with the MAC, the IP, the port, destination, MAC, IP, and port. And then we're going to write that packet to the destination network card. And then, so that's going to just keep pinging and encoding, send, encoding, send, encoding, send every second. And then also at that time, I spin up another Go routine here. And on that connection, I want to receive the transaction timestamps from the kernel. So every time I send a packet here, it's going to get looped back to me again over here. So I'm going to get this packet up here that I encode, I'm going to get back again like I'm listening it for myself. But additionally, this received TX timestamp will return the timestamps that the kernel and the hardware got it. And then further down, that's where I'm just sort of logging out what the TS hardware unit nanoseconds and what the format is. So that's on the sending side. On the receiving side, luckily I can do this all in one swoop. I don't have to start pinging and sending out one and then starting another like listener for the transaction side. I can do it all in one receive. So I can start listening like a TCP con, like accept. So once I get something, then this is actually going to get called because this is a blocking call here. I'm going to get the incoming packet that I got, and it's also going to return the timestamp at which everything came in. So this is where I mentioned like so once I get past here, like this is actually when I received the packet. This is how you would typically measure how you would receive a packet. You then decode it. I can pull out the payload that I got out of it. And then this is where I log out the user space, hardware, and software. And the delay computation is here. So I have the software, and if I subtract the time that I received it here, that's where that delay occurs, that 300 microseconds that we saw. So we're seeing that there is a 300 microsecond delay between the kernel and this actual log line that we get to time. And then also additionally, just for sort of complete list, there's a way you can get statistics out of the kernel as well. So you can keep calling stats every 5 seconds, and you can get how many drops occurred on the kernel, how many packets were actually sent in and out of the socket, and how many times the queue might have frozen. These are really beneficial if you're doing really high rate probing like lots and lots of packets, like every 10 milliseconds or so, like out the same network card. Every second, it's really not going to see any issues, but it's sort of a nice way to get stats on the socket itself. But yeah, that's sort of like the gist of what we were been working on, and how this actually related to what we were doing at Subspace. Is we had 130 servers that were shuttling traffic for customer traffic, and each one of those servers had 10 network cards. And I was working on the telemetry team that would probe from server A, network card number 1, to server B, network card number 3, send a packet that is IPv4 UDP, v4 TCP, v6 UDP, and v6 TCP. Send those probes once a second, all the time. And so this is what we came up with to sort of make that a little bit easier for us to create these listeners, so we can legitimately specify, I want to send a TCP IP4 UDP packet literally out network card number 1 out of 10 to that network card on the other side, and take the measurement. Is that a question?
Yeah, it's me again.
Sure.
Did you consider using IPCAP as a solution? I know this is much better than what you can get out of IPCAP, but just to understand what was the rationale, if you tried something with using Wireshark as a library, for example, before going
Yeah, we did,
that
but
bit.
yeah, we did consider that, but that was more manual. This was a service that was running 24/7, 7 days a week, 365 a year, and we're constantly sending these probes out all the time. There may have been a different method to do that, but another reason why we chose to do it this way is we had a way to speak to this telemetry service that says, oh, a new POP came online, so go add it to your list of destinations that you need to go and probe. So we didn't have to stop this service and restart it, or sort of make any sort of static changes to it. We could just let it run, and we could talk to it remotely and say, okay, you've been probing these 10 servers, now probe these 2 more that we just spun up in a different region. And then we just pick them up and start doing it.
Isn't there some variability that you'd have in the context switch to time now that
Yeah.
you'd account for?
Yep. That's why because of that context switching, we didn't really want to rely on time.now all the time. So we wanted to know, because we were shuttling customer traffic through eBPF filtering and port forwarding, customer traffic never made it to user space. We wanted to measure hardware network card to hardware network card. So using time.now was just adding unwanted latency, jitter, and packet loss. And so those weren't true measurements, which is what was the result of this. We want hardware to hardware. What is the latency of that measurement?
Blaine, when
Yes.
it comes to Dockerized applications, because please don't. I'm really you're blowing my mind here with all this information. But I think that most of us in a real life scenario will have to deal a lot with the traditional container applications inside containers. Would you have any advice for us to take benefit of what you're sharing with us when it comes to applications running inside containers?
There's probably a use case for that. So you could, because of the way Docker is running, this might not be a use case to get those timestamps, because Docker does not have a network card and Docker does not have the kernel. And in order to, because these are making lower level syscalls, you saw over when I was running the example, I had to run sudo.
Yeah.
You need
Yep.
escalated privileges to actually run the binary, which Docker probably wouldn't have. So there is no way for this to actually work in Docker to get those measurements, because Docker is running in a virtual environment which is sitting on a shared kernel. So, and that's sort of the point of those containers, that isolation aspect. But if, like in our case, we literally had dedicated hardware with 10 network cards, like we knew we owned the entire hardware stack, so we could take advantage of using this this technique.
See, there are some situations where you can run a Docker container with some special privileges. I know it will not be capable to measure on a by container approach, but if still you want to run such a server inside a container, did you give it a try? I mean,
I have not, so I would be really interested in it. Yeah, maybe that's something I can add to the example and see if I can get it working.
I think that Mike has just shared some stuff related to capabilities, and that's
Cool.
as a matter of fact, you can run some stuff inside the Docker, but telling, hey, I know you're a Docker, but go there and talk to the kernel yourself.
Yeah, it would definitely be interesting if it would work. So if it works, great. But then I would be interested to know, well, what are the times that I'm getting? Are they something that I can actually rely on as truth? Like, what do these numbers represent? Anything that I can use?
Yeah.
And so that's where I would sort of poke more questions. If we can get it working, it's one thing, but if it's giving us timestamps that don't give us any benefit, then it might not be worth actually
You're
collecting
right.
them. You know what I mean?
Yeah. And that's actually, please go ahead. I'm talking too much.
That's good. And I guess sort of something to add to that is sort of what's the point, right? Because you're trying to measure time from NIC to NIC. Why you don't even need to run that in Docker? Like, what, Docker doesn't really become part of that conversation because it doesn't really seem relevant anyway.
Yeah. Right. Yeah. There's definitely a use case there. Yeah.
In the case of the virtualization, the Docker stuff is not quite virtualization, but I assume that the hardware messages that you're missing are an implementation detail, and it's just a factor of whether or not they've done that.
Right. So the missing hardware times, because it's a virtual machine, there is no real NIC card. Like, my real NIC card on my laptop is further down, so I'm not getting those, and there's no mapping to that. I tried running it locally because I do run a Linux machine locally. My actual network card in my machine does not support hardware timestamping. So another caveat is you need a network card that you need to enable with the control message when it boots up to say, okay, I want you to start timestamping packets at the hardware level as they come in. If your network card does not support it, then you're not going to get them.
Got it. Thanks.
You mentioned that you were using a BPF to make the routing of the packages and everything. I was expecting that you would show us some eBPF stuff also to make the timestamps to get the timestamps. Did you ever thought about that? Is it possible? I'm not really.
If you're writing eBPFC to get loaded into the verifier and the kernel, I do not believe that there's a way to get the actual timestamp in eBPF land. There is a way to get the time at which a packet came in, but it's seconds since the system started, so it's not a true timestamp. So you have to know when the system started, that you have to pass in to the BPF program to say, okay, it started then, so first packet is going to be second 1. You're just going to have a number, so you need to know what that offset is from real world time. So again, that's why we had to do the control messages to get those timestamps out. There is a way to do it, but it's a lot of very interesting eBPFC and offsetting, which it was just easier to do it this way. But definitely it can be done. I've seen it.
Blaine is still on the virtual side of things. Are you running this on bare metal, or are you running, or did you give it a try on top of VMware and things like that?
This was running on bare metal. What you saw here was running on VirtualBox and Vagrant.
So to that level, that's agnostic. It would work as well.
Yeah, you need a full virtual machine for it to work. Yeah. Docker would be awkward and quirky, and I would be interesting to see what kind of control messages you get out of it.
Hmm.
But yeah, to get anything that makes sense, you need a virtual machine.
Okay, I see. Cool.
I did forget to put up one sort of slide. If anybody wanted to reach out to me after the fact, sort of like leave this up, you can reach out to me. Website, Twitter, DMs, GitHub, whatever. There's my email somewhere out there as well. Let me know. I'm also in the Go Slack room in networking and performance channels and stuff like that. You can DM me there as well.